Brilliant. Thank you. Good morning. Thank you, everybody, for that great introduction, especially to Manuel. Thank you to Michelle for asking everybody to keep questions to the end. Please ignore her. Right? If I say something that you don't understand, the best possible thing you can do is ask a question. That will help me, that will help you, and it will probably help a lot of other people in the audience that have the same question. So will you do that, please? Yes. Okay. Thank you also all for showing up so early in the morning. I know Melbourne has attractions that might make it harder to get up early in the morning. As a token of my thanks to all of you, I'm going to give a gift to one of you. So, what have we got here? Dave, this is for you. This is some cachaça, straight from Rio de Janeiro.
Thank you very much.
And if you need a lesson in how to make a caipirinha, ask me later. But this is what cachaça is for, caipirinhas. Who's had a caipirinha? Okay, that's much more important than using type classes. Okay, so Rio de Janeiro is a city whose streets are literally paved with lambdas. And while I was there, I'm not going to show you the rest of the talk. I did this. Oh, we can make that bigger, I think. Oh, can we not? I'm wrong. Hold on. View. Zoom. Oh. All the... Oh, is that what the issue was? Yeah, there we go. I thought that should work. Okay, there we go. I did this. So I wrote a book called Programming Language Foundations in Agda. And that's showing it at localhost, but let's see if the web is up. Yeah, there it is. So the exact same thing is available online. I'm just running it locally on my machine because I'm giving a talk, and who knows if the web will work. So the whole book is here, and what I'm going to do today, so this morning I'm going to try to take you very quickly through the key ideas in naturals and induction. So those of you that saw Bartosz's talk yesterday, I'm going to be covering the same ground, but I hope with more concrete examples that will be easy to follow. One of the things linked on the page is getting started. I'm going to show you that. So there's a section right at the beginning called Getting Started with PLFA. And this is exactly what you need to do. If you've done it already, please follow along with the talk. But as mentioned, there's going to be a workshop this afternoon. I will go through, again, induction and naturals, and I'll do the next chapter, relations. So we're going to do the first 3 chapters of the book today. Try to get very quickly through ideas in the first 2 now. So this is what you need to do, and in particular, pay attention to the bits at the bottom that tell you what you need to do to install the libraries. There's just a couple of files you need to set up. It's pretty straightforward, but you do need to follow those instructions. So, and one thing I want to do is ask for people who've used Agda before to serve as TAs this afternoon, teaching assistants. So who's used Agda before and was willing to serve as a TA? Fantastic. There was one other guy I spoke to yesterday, but he's being shy now. Oh, there you are. Okay. So we might have a couple of TAs this afternoon to help you out. I'll be very grateful to anybody who volunteers for that, helping other people get up to speed. Because there'll be I hope there will be lots of people in the room. And that way we can help you if you have any difficulties. Okay, let's go back. Okay, I'm going to get excited now, because I do. The night sky holds more stars than I can count, though fewer than 5,000 are visible to the naked eye. The observable universe contains about 70 sextillion stars. But the number of stars is finite. Count all the stars, and you will still have as many natural numbers left over as you started with. Right? There are lots of natural numbers, lots and lots and lots and lots. And that means if you want to define something like addition, even though you and I probably learned addition from little finite times tables, addition tables, when we were in school, and then multiplication from times tables, right? They're finite, and then you have these rules that let you work on larger and larger numbers, and it all seems really rather complicated. And if you tried to write out an actual table of all the addition results, it would take you a long time, because there are an infinite number of natural numbers. So this is sort of a problem, right? So what I'm going to show you today, which I think is really exciting, maybe not that exciting. What I'm going to show you today, which I think is really exciting, is that you can define all the natural numbers, all infinity of them, in 3 lines. And then you can take something like addition and take all infinite number of instances of addition and define it in 3 lines. So that's my goal for today. Show you how to define natural numbers, how to define addition, and then how to prove properties of all of the infinite natural numbers, such as that addition is associative. I'll pick that one simplest one, but the same proofs work and are in the book for things like commutativity. So clearly, right, when you first learn functional programming, nobody could teach it to you in an hour. Nobody could learn Haskell in an hour, but you could get a good introduction. Like Manuel gave a great introduction to Haskell in 4 hours, or was it 8 hours on Monday? 4. Right, so you can get started, but then you need to go back and do more work on your own. So my goal today is not to teach you everything about dependent types, but just to get you started, and just to show you enough that you might know whether this is something that's for you. So many people here, I think, are fans of Haskell, and I'm a real fan now of Agda, having written this textbook. I didn't know any Agda when I started. My graduate student, Wen Kalka, who's a co-author of the book, she helped me get started. But I'm a real fan now. I think that Agda is what Haskell wants to be when it grows up. And there are various bits in Agda that are just so much more fun for me than using Haskell. I'll show you some of that as we go along, I hope. So here's all the natural, well, I'm not going to write down all the natural numbers because there are too many, but here are the first few of them. And we're going to skip over that. Here is the definition in Agda. Okay, so we've got, so we're going to use Unicode, by the way. So you have data funny n. This is the way mathematicians always write natural numbers, which is a set where, so this is defining, so set in Agda is the name for types. So this is just telling you n is a type. I know SET is a very weird way of spelling type, but there you go. And then it has 2 constructors. So the notion of a constructor is very important and is separate from the notion of a function. And these are pretty much the only 2 things we're going to need to worry about, is constructors and values. And the values are going to include functions. So we've got 2 constructors. 0 is a natural number, and successor takes a natural number to a natural number. That's it. What does this mean? Okay, well, we now know one natural number, 0. And we also know one way of getting more natural numbers once you have a natural number. So suck, if you've got a natural number, it will give you another one. So 0 is a natural number. Okay, I now know one natural number, so I can take suck of it. So suck of 0, suck stands for successor, so the successor of 0 is another number, And then the successor of that one is another one, and the successor of that one is another one. So successor of successor of successor of 0 is a natural number, right? Altogether, how would you pronounce that natural number in English? 3, right. So that's just 3. Okay, so that's it. This idea alone is enough to get us all the natural numbers, right? It's sort of painful. So like writing out 7 would be painful. So here's a little exercise. Let's try doing the exercise. Let's see. So we need one more bit. Actually, I don't want to actually edit the textbook, so I made up another file. I could. I made up another file here. So let's do an example. Oh, and so we're going to do one thing. We're going to tell Agda that n is a definition of natural numbers. And that's because Agda has built into it, right? It looks at the data type and says, okay, this is the data type, in this case, n. But we could give it any name. We could call it Fred. And it says, okay, so Fred must be the set that's defined. And then there must be one thingy whose type is Fred, and another thingy whose type is Fred to Fred. And the thingy whose type is Fred, that must be 0. And the thingy whose type is Fred to Fred, that must be successor. And then if you write down 7, the digit, it knows that 7 means, let's try this out. So the whole textbook is written in a literate style. And that means that all the code you write must come between begin code and end code brackets. Everything else is just a comment. And so here, we're just doing an example. So examples always have the name underbar. And then the type of this example is going to be a proof that 7 is the same as successor of successor. Tell me when to stop. Is that right? 1, 2, 3, 4, 5, 6, 8. I counted wrong. Thank you. You guys were counting properly. Get all the parentheses to balance. And as you learned yesterday, the name of a proof of equality is REFL. And let me tell you how this works in Agda. Agda just takes the left-hand side and simplifies it as much as possible. So it knows 7 here is actually a definition for successor applied 7 times. And this is just a bunch of constructors applied to other constructors. So it doesn't simplify. This is already in simplest form. So it simplifies this, and it simplifies this, and it checks, are those exactly the same thing? And if they are, then there's a proof of that called REFL. And if there's not, there's no way to prove that. The set of proofs of that thing is empty, which means if it has no proof, it's false. Or at least we can't prove it's true. So this is something we can prove, and its proof name is REFL. And now if I type Control-C, Control-L, it executes. Here's the most important thing on this screen. See this little screen at the bottom? See that there's nothing written in it? That's very important. What you are seeing there is no type-checking error messages. So that means the whole file type-checked. So that means everything you've said is true. Right. Now, this is really true, right? This is checked according to a formal system. It's been formally proved correct. So as long as you got all your definitions right, and you've got your theorem stated properly, and the proofs are all filled in, and there are no type errors in the proof, you're pretty certain of that. Right? You're much more certain of that than, say, a statement made by Donald Trump. You're probably even more certain of that than a statement made by your best friend. Because your best friend probably won't lie to you, but your best friend is probably a human being and therefore might make mistakes. Right? Agda is, we hope, much less likely to make a mistake. Of course, it's a complicated piece of software, so there's that issue. What you'd really like to do is have a version of Agda proved correct in Agda. And that's an ongoing project. They're trying to get there. But they do have proofs proofs by hands of a lot of the bits of Agda. So that's the idea, is to try to actually have in your hand a proof that things are correct. So, right, the great thing is this gives you much more assurance. This gives you much more assurance that what you're doing is right. And sometimes you need really high assurance software. I will give an example later on in the talk. And those are the times when you want to do this sort of thing. Right? So you don't always want to prove all your software correct. But when you do, then a proof assistant like Agda, there are others out there as well, is what you want. There's a question. Can I show you a proof? I can show you a proof. Show you something broken? Sure. Let's go back to what I mistakenly wrote. And now it gives you an error message. It says 7 is not equal to 8 of type N. Good question. Thank you. OK, and then here's the same thing done for 2. We'll skip over that. Oh, wait. It's always going to give me an error message for this one. So let's just correct this one again so it doesn't get in our way. Thanks. OK. So the next thing to do is define plus. And remember, right, in school, you had a table, right? 0 plus 0 is 0, 0 plus 1 is 1, and so on. And then the next line was 1 plus 0 is 0, 1 plus 1 is 2, 2 plus 1, 1 plus 2 is 3, and so on, right? You all memorized that table when you were in grade school, right? OK, well, you didn't need to. Well, you did need to be able to do addition in, right? This is linear representation, right? So the number 1 million takes a million sucks, so that's really rather inefficient. Okay, but it's great for doing proofs. There's an exercise in the textbook about doing binary representations in Agda and showing that they're equivalent to the unary representation that we're using here. So this is very inefficient, but it's great for doing definitions and proofs. So in particular, we can now define addition in just 3 lines. So first we say plus is the addition function. It takes a natural number and a natural number and gives you a natural number. So this is just saying, here's the first argument, here's the second argument, here's the result. If you're familiar with Haskell, you'll know why we wrote it in this particular way. Otherwise, it's explained in the textbook. I'm not going to take time to do that now, but just presume, function of 2 arguments, this is how we write it down. And then there are little underbars here. Those are the places where the argument goes. So we can use infixed notation for defining things. So Haskell also has infixed notation. Instead of writing underbar plus underbar, you'd write plus in parentheses, and that's something called a section. And that gives you a nice name for the plus operation that's distinguished from its uses here, where it's in the middle of something. One of the great things about Agda is it has mixed-fix notation. So Haskell gives you binary. Agda gives you any combination you'd want. If underbar, then underbar, else underbar is perfectly fine in Agda. So you can define if, then else, and the arguments go in the right place. You can define prefix functions, postfix functions, anything you want. So it's very flexible, and I really, really like that. That's a great decision. It's too bad that Haskell has too many users to retrofit that decision into it. But it was a really nice decision that they made in doing the language design. That's, by the way, because they have an Arno Ranta, who's an expert on building parsers, so they knew how to parse such things. Question?
How do you then use plus as a prefix function in Agda?
Great question. How do you use plus as a prefix function in Agda? That's an example of a section in Agda. And rather than delay the talk now, leave that question to the end or for a break. OK, so here's the definition of plus. Does that work? Yeah. So we've just got 2 lines. Oh, actually, let's just comment this out. Let's just try to define plus for ourselves. Wait, yeah. Just move that off the bottom of the screen so you can't cheat. OK, so plus takes 2 arguments, m and n. and it's going to give something. So here's the other great thing in Agda, the whole. So this question mark here says, I don't know what to put there yet. Help me out. Okay, and if you type Control-C, Control-L, it helps you out. And it gives you lots of stuff at the bottom which we can ignore. It's just saying, here's some stuff I don't know how to fill in yet. If you find that scary, don't worry. Oh, right, it's getting, by the way, what it's doing here is it's saying, I've removed the definition of plus, and plus appears a lot later in the file. So this is everywhere else that plus appears. It says, I don't know how to type check this because I don't know what this is. That's basically what it's saying. But yes, sometimes you get lots and lots of error messages, which sort of look scary, but that's OK. Just ignore it. Actually, what I should do to avoid them, I can do this. In Agda, there's something that says, comment, uncomment. Oops, no, I didn't want to do that one, whatever that one was. What have I just done? Version. OK, we can ignore that. Comment, uncomment. So let's see. If I do it now, yeah, now it only says missing definition for plus, which is true. OK. And now it's happy. It only says one thing, which is there's this hole here, hole number 0, which should have a natural number in it, but I don't know which one. And now if we go into the hole and you type, what is it, Control-C, comma, it says, oh, and to fill this hole in, you can use two things. You can use n, which is a natural, and m, which is a natural. All right. So I'm going to need to do case analysis, right? Let's say I do case analysis. You could do it on the second argument. That's a symmetric definition. You could then prove the two definitions equivalent. In fact, what we want to do, and we'll do later in the textbook, is prove that plus is commutative. But what we'll need to do a case analysis. Let's do it on the first argument. So Control-C, Control-C, and that says, give me a variable to do a case analysis on. So I'm going to type m and return. Ha! It wrote a large chunk of the program for us. Yes, everybody should applaud, right? This is exciting. Right, that's so much fun. I'm just going to do that again. Yeah, everybody applaud this time. Control-C, Control-C, M, la 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 la, boom. Okay, so it said, well, there are two possibilities, right? Either m is 0, or it's the successor of something else, and let's give that something else now the name m. So this m is different than the m we had before. We could call it m prime if we want to, but I'm just going to call it m. OK? Is that clear enough to people? OK. So what is 0 plus n? N. Right? If you add 0 to something, it doesn't change it. So I'll type in an n there, and then I will go Control-C, Control space. It says, yep, that type checks. In fact, let's do that again. I can show you something else you can do in Agda. I can type Control-C, Control-A, and that means, can you come up with a term of type big N? And it will say, yeah, n works. So it actually wrote that bit of code for me. We'll try that one again, because that one's exciting too, right? OK. Control-C. You're all going to applaud, right? Control-A. There we go. Oh, that works so well. Let's try it again. Oh, that's not what we want this time, is it? We want something that uses m as well. So what shall we do here? Well, this is successor of something. So our result can't be 0. It must be the successor of something. So let's see. If we put in Control-C, Control-R, that says use a constructor, it says, no, I don't know which one to use. Should I use 0 or should I use suck? So let's tell it. Let's use suck, and then there will be something else to put in there. And oops, yeah. Okay, so now we've got another hole. Oh, what's the type of that hole? Oh, it's the same as before, right? Now I need natural number n, and I've got m and n available to compute it. What do you think I should put in that hole? Any suggestions? I could just put n in, but that won't give us the right answer, right? We want to make use of the m as well. What could I put in the hole? A recursive call. Okay, which recursive call shall I put in there? M plus n. What a great idea. Okay, so this type checks. Good. Does this give us, we think, what we want? So why should this work? Well, this is one more than m, and then we add it to n. This is we add m and n, and then take one more of it. So yeah, those should both be the same thing. Let's just do an example. Is it the case that 2 plus 2 is equal? Notice I'm typing Unicode here, right? This is actually backslash equal sign, gives us this funny equal sign. And then again, if that's true, the proof should be REFL. Yay! That worked. Let's see, does 2 plus 3 equal 5? Let's check one more thing. Let's check that 3 plus 2 is equal to 5. Yay! Those all worked. Let's check that 3 plus 3 is equal to 5. Oh, no, that didn't work. And right, the proof error is, again, it simplified this down to 6, and then says, no, 6 and 5 are not the same thing. Okay, so all that's working so far. And, oh, let's uncomment the rest of the file. Okay, now everything should work. Yeah. And here's a proof that 2 plus 3 is 5. So you can write proofs of equality in Agda this way. Later on in the book, chapter 4 gives you the explanation of how you define equality, which was something that Bartosz talked about on yesterday. And it also tells you how to define notations like this. But this is reasoning that you should have learned in grade school, right? You write one thing, and it's equal to something else, and it's equal to something else, and so on. We write these equals with funny symbols in them. Later on, this is because this and this, both Agda reduces them both to the same thing. It's just checking these all reduce to the same thing. So it's like what we did before, but now it's reducing lots of things and checking that they're all the same. Later, we can give some reasons for equality, and we'll see that in a minute. So what does this say? How do you compute 2 plus 3? Well, which of these two lines are we going to use to do it? Are we going to use the 0 line or the successor line? So 2 is the successor of 1, right? So it's going to match. Let's see, stupid computer checks. Is successor of 1 0? No, successor and 0 are different constructors. Nope, it's not that one. Is successor of 1 the same as successor of m? Ooh, it would be if m was 1. So I'll let m be 1, and now it matches. And so that matches 2, and then a plus matches plus, and then 3 matches n. Oh, that would match if n was 3. So it's decided here that m is 1 and n is 3, and it rewrites the left-hand side to the right-hand side. So then you get successor of 1 plus 3. Then we do the same thing again. Okay, does 1 match 0? 1 is successor of 0. Oh, they both have 0 in them. Maybe they match. Let's see. Is 0 the same as successor of 0? Oh, no. Successor and 0 are different. They don't match. Okay, that one doesn't work. Does successor of m match successor of 0? Successor and successor. Those are the same. So all I need is for m to be 0. And that does the same thing. It decides n is 3 again. So it rewrites a successor of 0 plus 3, and that's what we've got here. So 1 plus 3 rewrote to successor of 0 plus 3, and we just carry over the successor. And now, when it tries, does 0 match 0? Oh, I think it does. I think it does. And then n matches 3, so it rewrites to 3. So 0 plus 3 here rewrites to 3. So we've got the successor of 3. But 3 is just an abbreviation for successor of successor of successor of 0. So this is successor of successor of successor of successor of successor of 0, which is 5. So that's why 2 plus 3 ends up being 5. Okay, so that, some of you familiar with Haskell will have already seen this. This idea goes back to the 1800s. I think these particular definitions were written down first by Peano. They're certainly called Peano's definitions. Similar ideas were come up with by Dedekind in his paper Was sind und was sollen die Zahlen? What are and what should be the numbers? So this is not really a very old idea, using just 0 and successor and using proof by induction. Well, proof by induction, I get that. The Greeks knew proof by induction, didn't they? Who knows? Did the Greeks know proof by induction? Does anybody know a 2,000-year-old proof by induction? Okay, we're all ignorant, including me. Sorry? Before your time. Okay, I have to look that one up. I think proof by induction is pretty old, but I'm not sure. Okay, so next thing, right? So now you've seen definitions. Now we want to see proofs. So here's an example of a proof. So you're at a party and you meet an operator. You want to make small talk with the operator. How do you do that? Right? What questions do you ask when you meet an operator at a party, Dave? A binary operator, like plus, that you haven't met before. What's your type? Great question. Okay. Once you know its type, you might ask questions like, are you associative or are you commutative? So associative just means you can put the parentheses anyways, and commutative means does the order of the arguments matter? So if it's commutative, we would prove that m plus n is equal to n plus m reversed for all m and n. For associative, what it means is the parentheses can go either way. So that says something like 3 plus 4 plus 5 is equal to 3 plus 4 plus 5, with the parentheses the other way. So open 3 plus 4 close plus 5 is the same as 3 plus open 4 plus 5 close. Yes, question? My definition of addition made use of the fact that 1 plus is associative. That's why it's correct. But I just put it in by fiat. Right? Now I'm going to show that that's enough to make it always associative for all numbers. Good question. So this is bloody obvious, right? Is it really so obvious, right? Because 3 plus 4 is 7. So we get 7 plus 5. Well, that's 12. But the other way around, right? 4 plus 5 is 9. So we get 3 plus 9. Oh, yeah, that's also 12. But all of a sudden, when I look at this, I think, is it really obvious? So the way you make it really obvious is with a geometric proof. Right? If I have a line of length 3 next to a line of length 4 next to a line of length 5, I can first turn the 4 and 5 into a longer line, or first turn the 3 and 4 into a longer line, but no matter which way I do it, I get the same answer. But here, but that requires hand waving. Doing geometric proofs on a computer is possible, but tricky. Much easier to do an inductive proof. So, can we prove this by induction? Yes. Again, let's make that go away. Let's comment it out. Okay. So now, We want to prove using induction so we need to give a proof here. And how many people are familiar with proof by induction? Right, quite a few of you. How many people here are familiar with recursion? Right, that's pretty much everybody, I think. So here's the really cool thing. This is the takeaway that I would like you to get from today's lecture, which is definition by recursion and proof by induction are the same thing. Okay? You should all go, ooh. 1, 2, 3, ooh. Right? That's really amazing. When you do a definition by recursion, as we did with addition, why did that work? Right? Why is this better than saying something like, say, Brexit equals Brexit? Right? There's a definition by recursion, but that's what we call a non-well-founded recursion. Right? It doesn't tell you anything about what Brexit means. But when we defined addition up here, we defined plus in terms of plus. How could that be a right thing to do? But the reason that it works is because plus of successor of m and n is defined in terms of plus of m and n. So if this is 2, here, this will be 1, right? And that's why it works, because 2 shrinks to 1, shrinks to 0. The first argument gets smaller and smaller and smaller. And that's because we did pattern matching here, and m is part of the first argument, and then here we use it as the first argument. So when we do a recursive call, this is a part of the argument for the thing we're defining. So this is replaced by one of its parts. So that's called structural induction. You're replacing the whole by one of its parts. And that's why it works. So this thing is getting smaller. So we're going to do the same thing. We're going to prove for all m, n, and p that addition is associative, but we're going to do it and we're going to do it in terms of that very fact, but that fact on a smaller m. As long as your m gets smaller each time, as long as whatever thing you're inducting on gets smaller each time, that's okay. The other way we could do this is backwards, and we'd say we're defining plus on successor of m in terms of plus on m. So it's similarly, we're going to prove associativity of successor of m in terms of associativity on m. So it's a smaller thing. So as long as you do it on a smaller thing, it's well-founded. Eventually you reach the base case, which is 0. So that's what we're going to do, proof by induction. And we can do the same thing interactively. So we've got a hole here. I can do the same thing, Control C, Control C. Let's induct on m. Right? M is the very first thing, plus we defined by case analysis on the very first argument. So using the very first argument will work out well here. We could also define plus on the very last argument. If we'd done that, induction on P would be a better choice. So there we go. So what do we need to prove here? If we look in the whole, it says what we need to prove is that n plus, right, so this will simplify. Right, so m plus n, if m is 0, 0 plus n is what? N. So we've got n plus p on this side, and 0 plus n plus p, well, this is 0, so it simplifies to n plus p. So both sides simplify to n plus p. So what we need to show is n plus p is equal to n plus p. Okay, that's really easy. Right, that's just REFL, and we're done. It's obvious. But I'm going to write that out more long-windedly. I'm going to write it out like this. So I'm writing it out like this. So this is what I just showed you, right? We've got 0 plus n plus p. That simplifies to n plus p. And here we've got 0 plus n plus p, which simplifies to n plus p. Typically, when you write out these proofs, you do them so that one side is the top is the left-hand side of the equation, bottom is the right-hand side of the equation, and you simplify inwards. So as we go from the top to the middle, we simplify. As we go from the bottom to the middle, we simplify. So now, what's left to prove here? So let's look in this hole and see what we need to prove. Now we need to prove the successor of m plus n plus p is equal to the successor of, m plus n plus p the other way around. Right. So how did we get these two successors out at the front? So again, let me copy over the proof. Oops. No, we want this bit. La, 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 la. Yeah, it's best to sing while you code or prove. La, 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 la. La, la, la. Nope, that's wrong. La, 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 la. La, 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 la. Okay, so now we've got the same equation we had before, m plus n plus p equals m plus n plus p, but m gets replaced by successor of m. So now what we need to prove is successor of m plus n, in brackets, plus p, is the same as successor of m plus n plus p, in brackets, right? So we simplify. So successor of m plus n plus p, by definition of addition, is successor of m plus n. And then successor of m plus n plus p, by definition, is successor of m plus n plus p. And you saw Agda automatically did that simplification for us. I've written it out longhand, so it's easier to follow what's going on. Going top to bottom, again, successor of m added to n plus p is the same as successor of m plus n plus p. Okay. So now, what we need to do is show that m plus n plus p, parenthesized to the left, is the same as m plus n plus p, parenthesized to the right. That's what I'm trying to prove. But now I've got m at the front instead of successor of m, so it's on a smaller argument. So I can recursively call plus a soc of m, n, and p. That's the proof that this thing is equal to this thing. But now I want the two things equal with cong written in, with suc written in front. And the way you do that is you say cong suc applied to the proof. Cong is short for congruence, and suc, recall, is short for successor. And a soc is short for associative. So by the congruence of successor applied to the associativity of plus of m, n, and p, we get the desired result. And if I now type, oh, we don't. What did I do wrong? Oh, I left this little hole here. I shouldn't have done that. Okay, you've now seen how to show associativity. And there's another way of doing it, which I'm not going to talk about. Okay, we are done. Yay. Okay, let's go back to the textbook. So I've just gone through a very tiny part of the textbook. Thank you all for your help. I had no idea if I would be able to do all that in time, live coding. So thank you for your help. We actually are on schedule. So of course, to do that, I've left out loads of things that are in the textbook. And the idea is just to give you a taster, but you can now go back and look at all the other things in the textbook. Oh, I should. So there are things like the story of creation. In the beginning, there are no natural numbers. We won't do that. You can look at that on your own. And philosophy and history, and There's plus, and guess what? You can also define times in a very similar way, or subtraction. Exponent is actually left as an exercise for the reader, and there's subtraction. And then at the bottom, we get things like proving, well, currying, which is why we write this funny thing with arrows, and more of the story of creation, and more of the story of creation, and some examples of interactive programming, which you've now seen. And then there's an exercise, which is how do you do binary numbers? So doing binary numbers is an exercise in the textbook, not an easy one. If you do that, you're doing very well. And then every chapter explains what the connection to the standard library is. So all these things have exactly the same name in the standard library. That's usually the case, but I deviate in one or two places. And how to type the different Unicode characters. So like this funny n is actually \b capital N, and so on for all the other ones. But the other thing I wanted to show you is I want to go on to the next chapter, which was the proof by induction. Notice what our proof of a for all is. Right? We proved here. So the first takeaway, which is very exciting, is that induction and recursion are the same thing. But the other thing, which I just slipped by you without explaining it, and nobody found it confusing enough to ask a question, is notice I said for all m, n, and p, we have the m plus n plus p is m plus n plus p. And then our function takes 3 arguments corresponding to m, n, and p. So what is a proof of a for all, a universal quantification? What does it mean to say that for all m, n, and p, this is true? It means I've got a function which, given a specific m, n, and p, will be able to compute a REFL of the right type. It'll be able to compute a REFL that shows that this particular equation is true. And here, just writing REFL wouldn't type check. Right? We needed to do this recursive call in order for it to type check. So it's a recursive function that has the right type that shows that this type is always inhabited. It computes an inhabitant of this type. And in general, what does it mean to say for all m, n, and p that some property holds? It says, give me a specific m, n, and p, and I will compute a proof that that property holds for that m, that n, and that p. So we're actually computing specific things. Question? Sorry, which thing do you want me to expand upon? I don't know what you mean by congruence in this case. Kong-suk. I did explain that very quickly when I went through it. We need to show that successor of this thing is equal to successor of this thing, plus a soc of m, n, and p is a proof that this thing and this thing are equal. And then to stick why are we allowed to say, because this thing and this thing are equal, successor of these two things are equal? It's because functions are congruent. If you apply a function to 2 equal things, you still get 2 equal things if it's the same function. So this just says applying successor to both sides of this equation still gives you 2 equal things. Good question. Thank you. Okay. So this is the other really important idea, which is universal quantification is proved just by a function. Implication also is proved by a function. If I want to show A implies B, what I do is I say, given a proof of A, I can compute a proof of B. To prove A and B, as Bartosz mentioned, it's a pair. It's a pair of a proof of A and a proof of B. To prove A or B, it's a disjunction. It's the either type in Haskell. You hand somebody either a proof of A or a proof of B, and so on. OK, let's go 10 minutes. Right. No, don't do that. OK, I'm going to skip over some of this stuff. That's OK. Actually, I'm going to very briefly mention this idea because it's a really important idea. One of the things that you get for free out of using constructive logics like this. So notice, by the way, I said a proof of A or B is either a proof of A or a proof of B. And right, it's a data constructor, so you have to hand back one or the other. You have to give it a proof of A or a proof of B. Notice this loses something that we're familiar with from classical logic, which says it's always the case that A or not A is true. You're only allowed to say it if you can say which, right? Which is not always the case, right? Either Fermat's last theorem holds or Fermat's last theorem is false. You're not allowed to say that. You have to tell me which means you have to be Andrew Wiles and come up with the proof of Fermat's last theorem, which took 400 years. So answering A or not A, that can be hard. I'm going to show you a similar example of this, which is, right. So the second half of the textbook is all about formalizing programming languages using different variants of lambda calculus and typed lambda calculus. And in typed lambda calculus, we have two properties called progress and preservation. Now, there's something else, right, which is really useful that you'd like after you've defined your language. You'd like something that can execute programs for you. You'd like an evaluator or an animator, something that can do reduction steps and tell you what the answer is. And when I started writing this textbook, I was working at IOHK with Grigori Ross, who has something called the K system, where you put in a bunch of rewriting rules and it gives you an animation of them for free. And so I had K envy, right? I said, I want to get evaluation for free. But right I based a lot of what I did on a previous textbook, Software Foundations, and in there, they don't have it for free. They say, oh, I'll show you separately how to normalize things, and they define a normalize tactic. There's a paper called Functional Big Step Semantics, where they say, to test a semantics, one must actually use it to evaluate programs. And it says many small step approaches can do this, but they only cite Grigori Ross's work, which I just mentioned, and another nice piece of work by Robbie Findler and others called RedX, which is available in Scheme. So RedX and K can do it, but nothing else can. So now I've got K and RedX envy. And then in the Poppelmark Challenge, which was published quite a while ago, right, part one of it was prove some things using Agda or some other proof system. And the things they wanted you to prove were preservation and progress. So preservation says if a term is well typed and you reduce it one step, then it's still well typed. That's covered in much more detail in the textbook. And progress says if a term is well typed, then either it's a value or it can reduce. And then in the next section, they say do automation, do animation, which is a separate task. So figure out how to reduce a given term. What was not widely realized back then, and what I hope everybody reading my textbook will realize, as far as I can tell, this textbook is the first place it's published. People like Bob Harper have known about this for years. Bob Harper has this amazing thick textbook on semantics. Does this fact appear that once you've done a constructive proof, you've animated it? No, I asked him. It's not there. I said, why isn't it there? He said, well, you can't publish that 2 + 2 = 4. It's obvious. And it is obvious. Once you've seen it, it is completely obvious. Right? It's so obvious I will swear horribly and say it is bloody obvious. But nobody published it. And I didn't realize it until I was 6 months into writing the text. And I went, wait a minute. Preservation and progress are exactly what you need to get evaluation. And here's the definition of the evaluator. And basically, the idea is, remember, progress says it's either a value or it takes a step. It's constructive. It has to tell you which. So if it tells you it's a value, you're done. If it tells you it takes a step, you've taken a step. Now all I need to do is recursively apply it. Oh, but I need to know the thing I step to is well typed. Oh, that's what preservation gives me. So just by repeatedly applying these two things, Bob Harper told me I had a very nice name for this, the passe des deux, because preservation hands off to progress and progress hands back to preservation. Sorry, other way around. You start with progress, you preserve, and you get back to progress. Anyhow, you can write it up in this many lines. I won't go through it in detail, but it's very concise to write up. In a constructive language, like Agda, every program you write terminates. That's because Agda insists when you do recursion that it's structural recursion on something smaller. Anybody who's familiar with lambda calculus knows that given the right constructs like fixed point, you can write programs that don't terminate. So how do we make this work? We just give it an extra counter here, which is just a natural number, and you count down. So you always are reducing that, and that's what guarantees you terminate. If you don't give it enough gas, you won't reduce it to a normal form. But you can take what you get, give it more gas, and keep reducing. It's called gas because that's what we do in the cryptocurrency field. We call it gas. So the name is stolen from Ethereum, where they use a similar trick to guarantee that when you send in a smart contract to the blockchain, it doesn't take forever to evaluate. And there's an actual reduction of a term in lambda calculus computed by this evaluator. And the textbook, of course, has lots of examples in it. They were actually very hard to do by hand. So I was really pleased when I realized I can compute these all automatically. And so that's what I do. I reformat them a bit, but they're all computed automatically. OK, very quickly, I have 3 minutes. OK, very quickly. We've done all this at IOHK, where we've got a smart contract language, which Manuel told you about. Here's the team working on it all. These people are all fantastic. But I'm going to focus on the work of one person, James Chapman. So James' PhD thesis was about proving properties of programming languages in Agda. He's the world expert on this. We have our own very simple language, System F, which is based on lots of work by different logicians who discovered the same thing independently. But I won't go into that in detail. But the logician Jean-Yves Girard and the computer scientist John Reynolds both discovered System F within a couple of years of each other. So that is the core language that we run on the blockchain. The idea is pick something 40 years old, and maybe it will be good for the next 40 years. So there's the complete syntax of it. It's a little bit more complicated than what Girard did, but not much. It's a derivative of what Girard did. Girard did System F omega, and we have a derivative called System F omega mu, which also has recursion, because we need recursion. There's the whole thing written out in Agda. The key thing is, the lovely thing is, in the cryptocurrency field, it's so important to get this right that there are actually several firms out there that have done proofs in Coq that their core system is correct, or are in the middle of doing proofs in Coq, another proof assistant, that their core system is correct. So when I went and said, we should do a proof in Agda that our core system is correct, right? It's 40 years old, but let's do the proof in Agda. And they all just said, yes, of course, we should do that. And they hired James to do it, and James has done an amazing job. Here's another colleague of mine, Roman Kiriv, saying what a wonderful job James did. But this is a cool thing about cryptocurrency. It's so much money that people are willing to use functional languages to get it right, and willing to use proof assistants like Agda and Coq to prove they've gotten it right. So we actually now have a commercial application. OK, I'm done. If you want to learn more about this idea that people have been alluding to, that data structures, like records, are the same as logical things, like conjunction, that things we do in programming all the time, like functions, are the same as logical things, like implication, then have a look at this paper, Propositions as Types, except you're all young, so you don't read, but there's a video as well. So you can see it on YouTube, the recording of a talk I gave at Strange Loop. And I'm done.